Hello. Today we're going to be talking about the use of functional abstraction, that is, wrapping code up in functions, with a particular eye towards procedural language such as C, and particularly how that can benefit us in terms of managing the complexity associated with reasoning about what we call side effects, cases where a program updates its state in some sort of way. Such as writing a file to disk, such as writing to a variable, that is to say, incrementing a variable, such as writing a different variable into a pointer that points to some data structure, such as a binary tree, or cases where data is sent out over a network. So we use this term side effect within computer science to mean an observable change program state. I won't go into it here now, but there's some subtlety here because we'll also talk with a side effect with respect to some user of that code, for example, or with respect to some frame of reference. That's a subtlety I won't go into right now. So the presence of these sort of side effects, writes through pointers, writes to variables, etc., can greatly complicate our reasoning about how a program works. We'll see some particular examples of that shortly. And it also can have an adverse effect on our flexibility in changing the program. Can really slow us down because we look at the code and it's a tangled mess of things, and to really evolve it to, for example, separate it out into two pieces, to move code around or insert new code, it's a lot harder because we're afraid it might break something. That's because these side effects are associated with dependencies, and they require that certain statements need to go before other statements. And because of this, when we look at a longer stretch of code, there's often a lot of things hidden in a sort of tangle of details. Which value another value depends, what is changed by this value, or what it computes. It turns out placing codes in a function makes this sort of information much easier. We can see very clearly on what external values it depends, because those are the parameters. We could see what it changes much more easily, because those are the things that are written and visible outside that function. So in a language like C, that would be things that are in global parameters. And what it computes, well, those are the things which are to be returned from it. So let's see an example of this. So here's a bit of code that's doing a bunch of things. Now, when we glance at this code, at first, we try to kind of figure out what's going on, and we look at it and we say, okay, this is a variable here, and I guess that's initialized there, and somehow we allocate this, and that depends on some variable here, and then we have an update. It's an update to that thing. In short, there are these dependencies. This guy depends on this guy having been allocated first. Total revenue is in fact what we calculated up here. That might have been easily missed. So this guy has to go after this loop. It depends on it. And similarly, and for some reason it's not shown clearly, so I'll make it more clear. There are certain variables, for example, which are the same variables. This variable is the same one as that one, count city. So these loops are iterating through using the same count of upper bound for upper limit for I. I never actually reaches this, but it goes up to that -1. Similarly, this guy is the same as that guy. And when we first look at the code, that's not obvious. We have to kind of look at it and trace and say, okay, yeah, that's the same. Oh, this guy is that one. It's not immediately obvious. Here's another example. So we have some loops here, and we're computing some quantities, and once again we find ourselves sort of needing to stare at this and kind of figure out what's going on. Okay, this guy's the same as that guy, but oh, those are not the same. This dot product, oh, that's what we calculated up there. So once again, there's all these different dependencies. Now, why are these dependencies important? Well, among other things, as I've mentioned, they affect kind of what we can do with the code. For example, the code here in this area cannot be placed before this computation of magnitude because it depends on magnitude. By contrast, we could actually place this normalized x allocation before this computation of magnitude. In fact, it could be placed way up at the top. It doesn't depend on any of these things. Similarly, if we were going to change some of this code, we're thinking about, for example, changing how we allocate this or where it's allocated or whatever, we'd have to be thinking about what depends on it. So what things we can move around, where we can move them around to have really strong, we have a really strong need to understand these dependencies to figure out what we can do legitimately. Where we can insert code, for example, that changes magnitude, we need to see, okay, well, what depends on that value before it's changed, etc. Similarly, even when we've gone and improved code, folks in class remember we improved this expression by kind of unpacking it. But even there are these dependencies that limit sort of what we can do before other things. For example, we can't move this code before this area because it's got to use the result of this. We can't just easily sort of separate it out trivially to be placed it in a different place where this code might not run before it. So even code that's sort of cleaned up, we often have these dependencies. We can't decrement this variable k before we've actually used it. We also saw earlier in class some of the complications associated with for example, code that includes side effects. So here we have a call to insert, which has two calls to read, and read modifies the value that's pointed to by these two things. And we noted this can cause a lot of confusion because read has a side effect, namely it reads from a file and reads the next data item from the file. So which goes first? You know, if this one goes before that one, all different effects. If this one goes before that one, the file will be read in different orders. And this is a problem because of read has side effects. If read was just, computing pi or computing some value, we could call it twice and it would just return the same thing each time. That wouldn't be per se a problem, except we want to consider performance at some point. Okay, so we've seen a bunch of complications associated with side effects. The main thing I want to highlight here is the cognitive overhead associated with kind of figuring out what the code does. What is the same as what depends on what, and by implication, what can be moved around to where, etc. Now, this cognitive overhead is no small thing. It causes a lot of problems. It causes slower debugging. It causes slower understanding of how to test something. It causes a real slowdown in understanding the code written by someone else or yourself a long time ago so that you can modify it safely. But even worse, it's associated with bugs. If we don't clearly understand what depends on what, we may do something silly, and that may break the code. For example, we may have an update to one of these variables after it's used here, or after it's computed here. We may have an update so that it's used. It doesn't get the value that was computed here. Another thing is we might move this code fragment below this, and then this would be using an initialized a variable that's initialized to 0 here. So there's non-trivial implications of this sort of cognitive load. It causes quality problems, it causes confusion, leads to frustration, and this may seem all straightforward, but it's needlessly a burden. And late at night, when you're working on a big code base, you've got a lot of bugs to fix, or what have you, dealing with this cognitive overhead is just can have very, very undesirable, feelings of stress associated with it, etc. So how do we deal with these things? Well, one of the best ways to do it, to lessen this sort of cognitive overhead, lessen the sort of troubles we have in reasoning about large sets of code, is to break these into small functions. These make far clearer what depends on what. It makes it much easier to read, far less daunting, far less tangled. We don't have that sort of tangling up of dependencies which force us to sort of stare at the code for a long time to finally grok, okay, what it's doing, so then go and modify it. Instead, it's much more evident, and we don't have to look at all the details unless we want to. Those details are hidden off in other functions. Even better is if, when we carve off these functions, we use specifications for them. I'm not going to be talking about that this lecture, but these will be brief statements, not about how that code works in a detailed sense, but what it does. What's its job? So, what job does it perform? What does it accomplish? And we can often specify that what far more easily than the how. Another thing we'll look at is the use of functional conventions, cases where we'll simply have functions that compute values and return them. And those values that they compute might be a so-called scalar quantity, a quantity that's simply a double value or an integer value or what have you, or it might be in fact an array, for example. Another thing we can do is adhere to really good naming. We talked about that before, and we'll mention again a bit later, segregated pure functions and commands. Now, another broad topic I don't have time to discuss, but some of you may be interested, is these sort of functional conventions are in many ways inspired by the cleanliness associated with functional languages, languages which support what's called equational reasoning, cases where we can much more easily reason about dependencies because they are transparent. So let's replace this, see how we can improve this code through a functional style. Replace this code with other code where the dependencies are far, far clearer. So we have this code up here, where we first had one loop, and then we had this allocation, and we had another loop. We had to sort of trace what depended on what. Now imagine replacing this code by what we'll call functional code, where one set of values depends on another set of values in a totally transparent way. So here we have a call in this better code. We have a call to this function normalize array, and function normalize array takes 3 arguments, and the third of these arguments is a call to this function called array total. So array total, this might be expected from its name, totals up whatever's in this array, and then takes that value and passes the same array, the number of elements in the array, and that total to normalize array. And normalize array just divides each element here by that appropriate total that we computed, and it creates a new array from that. That's what this code up here is doing, but the dependencies are clearer. We know this normalize array. Before we call that, we have to call this array total. And all the work that's being done up here gets done here. It's just a lot of it is hidden. It's hidden in normalize array, for example, or in array total, in ways that we don't have to look at them unless we have to. So here we could talk about equational reasoning. We can simply reason mechanically that, okay, calling array total, its job in life is to compute the total of this array, and then it just gives back a value. We don't have to reason, oh, it's changing this global variable or what have you. It just computes a value. Count cities is a value. We used it up here. Excuse me, I should say count cities, not count gyms. And similarly, array revenue for cities, it's a value, it's an array, it's a pointer to an array. And this, in turn, returns a value, which is another array. It's a pointer to an array, which has the results of this normalization. So the normalization depends on the total. And that's true up here. This normalization is depending on the total. But what's going on is not so clear here. We have to sort of unpack it. We have to sort of sleuth it down, and in the process kind of notice these connections among variables. Whereas here they're much more evident. It's not perfect, but they're much more evident. We have far fewer of these dependencies to worry about, and they're more manifest. Some people might prefer something like this. We have a call to array total, and that gives us total revenue, and then we normalize this revenue on a per city basis by this total revenue. In other words, we divide it by that. This code is used an extra variable, an extra line, but the name of that variable is clear that we're dealing with the total revenue, which, may have a conceptual clarity. Okay, so here I should note this normalize array, for example, if you want to consider that code. Why is this? Well, it may be evident that it's clearer here, after all, going from a longer bunch of code to a smaller bunch of code. Case where there's a lot of cruft, a lot of confusion, a tangle of different details here among variables, just something which is cleaner. One computation that computes this, and another computation that then uses the result of that, these other things to compute a different thing. It's cleaner, but someone could say, well, wait a minute, all you've done is you've shifted the risk, you've shifted the burden. Now the gross things are a normalized array, and you're not showing that to us, for example. They're an array total. Let's consider that. In fact, I would argue that while it's true that normalized array incorporates the code from here, in fact, from here, these three lines, in many ways it's cleaner. You'll recognize those lines. This line here with the calec corresponds to this line. This for loop corresponds to this. Okay. So why do I say it's cleaner? Well, what's cleaner here is that it's much more obvious what this code depends on. I mean, here we have to kind of go trace that back. Okay, this guy depended on that guy, and this guy is the same as that guy, and this one is the same as that. To really figure out what was going on, or figure out how to modify it, we have to sort of trace these things. Now, what it depends on is evident. Okay, there could be a global variable. In this case, there's not. Instead, and it's better practice if there's not. It's better practice to just have this code. Far better practice to just have this code depend on what's passed in as arguments. These parameters here, formal parameters, specify what information is needed for this function body to do its job. This is what's needed for it to do its job. So when we're considering the code in here, what it depends on is evident. It's in these formal parameters. This is what it depends on. Okay, so for example, there's a source array that it depends on, There's a count of elements that it depends on. There's this denominator that it depends on. Ladies and gentlemen, that is just not obvious here until you kind of really study it. Here it's listed out for you in detail. It's listed out for you one after the other. Makes it very obvious. What does it need to do its job? And that, ladies and gentlemen, will be the key part of what we call its contract. You give normalized array these things, it will do its job. And that job is implicitly specified by its name. It's best specified by a specification, which is something we'll talk about. It can be either formal or informal. So the dependencies are clearer. So we're not merely moving grossness around, moving ugly things and hiding them in this. There's a little bit of that. After all, here, no one has to look at normalized array unless they really want to. Hopefully the name is clear enough, or at least comments associated with the .h file make it clear what this does, so that you don't have to look at it in most cases where you're using it. And that's an advantage for sure. But it's also, so it's nice that we don't have to look at this code together with this other code. But when we look at this code, it's just more obvious how it works because the dependencies are there. You don't have to look at it unless you have to. The code that calls this function is to a degree self-documenting because it's calling normalize array. If we had a comment over here that said normalize the array, it would be a little bit redundant. I mean, it should be fairly evident through the naming. Many places in the code now can use this function. The fact that we've carved this off like this in this normalized array means that we've now enfranchised many other places in the code which can now use this common set of code. So if we have other code which is normalizing different arrays or what have you, we don't have to just copy and paste this code. We just call this function. And more to the point, if we have a faster way of doing this, or a cleaner way, or a way that takes advantage of hardware to minimize the computational footprint in terms of memory or in terms of so-called cache, we can do this all in one place. This code could be modified without changing the code that depends on it, that calls it. We can change the internal details of what's going on here without changing what's calling it, something like this. So the fact that we've wrapped this up in this function has a variety of different benefits associated with it. Similarly, if we had something like this was the second example. Look at that tangle. Look at that set of dependencies. This is the sort of code I don't like to look at, even though technically this is, 10 lines of code. It's unnecessarily ugly. It tangles you up. It forces you to kind of look at it and tease out what's going on. It's just not so obvious. Ladies and gentlemen, if you see code like that, think abstraction. Think, can I create functions for each of these little pieces, maybe providing some additional parameter or two so it can be used many other places in the code base? And can I give them nice names so that I don't have to go look at all this sort of detail? Okay, so rather than this, we could have something like this. We could have call to normalize array. So normalize array again, which takes x and then it's normalizing by something which is the magnitude of x divided by the dot product of x and y. So ladies and gentlemen, here, once again, we have functional code. So this is called first, it returns a value. We don't have to worry about it more than that. It just cleanly returns value. It doesn't change something that we have to worry, oh, now it changed something. And, we can't put it before something else, which is depending on the thing. It's just calling off to this, returning a value. This is calling off to, so that it computes the magnitude of this vector x. we divide the values, and then we call normalized array. On that, it computes a new array. So it's normalizing the array x by this value, and then we get a normalized x out. Again, the dependencies are clear. They're defined by the sort of the natural calling structure here. This calls, this, in order to call this, we first have to call this, and then we have to call that, divide them, and then we can call this. So the dependencies are much more clear than they are up here. In general, it's less puzzling things to look at. The names make it more obvious what's going on here. Okay. So why use functional abstraction? I've referred to this, but I really want to sort of convey these points. And forgive me if I repeat them a number of times. Students tend to forget these things when it comes time for a final exam or a midterm exam. So why use functional abstraction? Well, we just talked about a number of reasons. Easier modifiability. There's only one place to update when we change something, when we change how we want to normalize the array or what have you. Transparency. What the code does is clear. The code that uses that function is clear because the name makes it clear what is going on here, at least a lot clearer than these sort of things. This is a normalizing of the array x that's going on here. It's cleaner than trying to tease it out and figure out what's happening. And it's reduced clutter through the code. We don't have to look at all the gory details of these computations. It's easier to reuse later, to call it from many other places in the code. And the lower complexity lowers the risk of programming error. And in fact, it's modular. Why do we prefer this modularity? Why do we divide it like dividing it into pieces that are articulated in key ways? Why do we divide it up into these modules, speaking informally, to these little individual elements, these abstractions which each capture a certain amount of functionality? Well, there's a lot of reasons for it. Among other things, it allows divide and conquer. So I can do one of them, you can do another. Or we could have a team and have 5 different people working on different pieces. The other, consider a given person, a given software developer working on one piece. The others don't need to know all the gory details of it. They just need to know the contract. When you call it, what does it need to do its job? And when it's given those things, what does it do? What does it do? Not all the details of how. That's for that software developer to figure out, but they just need to know what it accomplished. It also allows for separation of concerns. We put things that don't have to be tangled together in different places, so we don't have to think about them all together, treat them all at the same time. Instead, we place them in different places. And finally, as a means to reuse, as a means to being able to reuse the code in different places from the code. So these types of benefits will accrue benefits collectively throughout the length of a software project. So when you're creating the code, when you're modifying the code, when you're testing the code, having it in nice small pieces lets you test each of them independently rather than testing a tangled mess all at the same time, which is like trying to adjust undo a very tiny screw like on the back of your computer with a small fine jeweler's screwdriver using a boxing glove on. Testing, it's much easier to break it up into pieces, each of which we can test independently, and then we test them together. It's easier to review. It's easier to have staff that sort of specialize on different pieces. Another reason we carve things out into these pieces, into sort of functions like normalize array or what have you, is that things change. Sometimes our requirements change, sometimes the technology changes. sometimes our understanding of what's best performance-wise change, etc. And by carving these things out into pieces, we don't have to go through all the code base and change it at many, many different places. We can change it one place or just a small number of places it's contained. It may be a big change conceptually, but it's all localized. It's all contained in one particular place. So we choose abstractions will hide the details of things we anticipate will change frequently. And that allows those changes from propagating to many different places within the code base. We talked about reuse, and it turns out there's many types of abstractions. Now, many types of ways of doing that many of you will see later in your education or career functions, but also classes, and also cross-cutting functionality can be captured with what are called aspects. And later you'll see what are called parameterized types and generics in other classes or in professional practice in languages such as Java or C++. Called templates there. Okay, so we've talked about these abstractions like normalize array, sort of an operation that we carve out and put in a function. What's the role of these sort of parameters in it? Well, it turns out sometimes if we have those parameters, we can often use it from many, many different places by giving it different parameters. So just to give a sort of trivial, simple example here, you notice we gave normalize array 3 parameters. We did not create normalize array specifically to divide array revenue for city by total revenue, assuming the number of cities was count cities. We instead created a function that we provided parameters to, and that allowed this function to be sure to be used here, but allowed it, the fact that we sort of abstracted away from, as we're saying that, which particular array we were going to use it with, allows us to call that code from elsewhere. The fact that we abstract away from what particular count of elements, we didn't hard code the fact that we were doing it by count of cities, allowed us to call this code from many, many different places. For example, from here as well. We can reuse the same method. Ooh, no, that should take an extra. Excuse me. It should count. This takes count dims. Oh boy. Now we got the joys of PowerPoint. Okay, so we gotta go line this up nicely, as is an idiom. So the fact that that we give it these different things, we didn't hard code it to depend on some specific specific things here, is what gives it much power, because we can call it from elsewhere, for example here, and provide it with different parameters. It allows that abstraction to be reused at many different places, many different contexts. The behavior of the function as a general rule is overall sort of a similar type of behavior. It's just the details of exactly what its assumptions are different, because we're using different parameters. And I want to again emphasize that if you're going to carve off these functions, give them nice names. Use names that clearly indicate some sort of meaning associated with this. And that's extremely important, because we don't want the user to just have to go back and go immediately to refer to this function, find out what it does. If you called it n, if you called the function n instead of normalize array, or if you called it na, they're not going to know what it does, and they're going to have to go look at this code. And you've undercut, you've almost eliminated there one of the big motivations for carving this off, which is that we don't have to look at it where we're using it unless we need to. It should be self-documenting, and a good name is absolutely key to that. Okay. And a final suggestion, which I had mentioned before, is separating these methods into pure functions. We just saw these pure functions. These are functional things. They have no externally visible side effects. You pass them an argument, so you pass them this, normalized array computes value, which happens to be a pointer to a new array. It doesn't change anything. It computes something. And as a result, if I had several of these in a row, as long as if they're computing different things and not using each other's return values, I can call them in any order. It's easier to reason about. Fully modular, we can call it twice without worrying it's going to give different results. Here we're often running our sort of major algorithms to deduce things, query data from a database or whatever. It's often really, really easy to test. On the other hand, we may have certain commands that are called like update array, or display customer info, or order book, or what have you. And these should be commands. They should have minimal computation with them. Don't mix the two. We do our computation in one set of functions. We do our commands in another. Now, this is not always a division which we adhere to because of performance reasons. There are cases where sometimes it's highly, highly advantageous to do some computation at the same time as we're updating something. But frequently, this is highly desirable to separate them. And that allows us to have greater clarity on what this accomplishes. And it simplifies testing, etc. Okay. Now, I want to note that I gave some examples here. Functional abstraction where it computes a value and hide. Very, very simple algorithm. But you should also carve off these sort of functions to test some condition. For example, if you have conditions in your code under what, is this a legal coordinate, or is this is this a legitimate customer, or what have you, rather than testing those things directly in the code with a long expression, carve that off into a function. And chances are you may be able to use that many, many, many different places, because there'll be many places in your code where you'll say, is this coordinate legal, or what have you. Here, one of the best things you could do is take complicated conditions, which are just puzzling to look at, confusing, people may not be sure what they really mean, and put it in a function that says, is check delinquent, or something like that, so that instead of looking at a condition as 4 different situations which it's considered, if it's too old, or if it has no, if it's to a bank account which is known to no longer exist, or whatever, then rather than sort of looking at those conditions right in front of us, put those in a function, give it a call as is check delinquent. And you might be able to, again, use that for many, many different places. So, ladies and gentlemen, I've provided some discussion here about motivations for carving things off into functions, why we put code in functions, and how we can use that to help manage this complexity of side effects. The fact that we're presented with these welter of details when we look at code, and particularly if we're tired, particularly if we're stressed and hurried, particularly if we're under pressure. Look at this sort of complexity is a nuisance, can add to our stress, and can just invite bugs. So rather than looking at this kind of tangled sort of web of dependencies, let's carve them out into clear functions, which we can call them very, very clear, and where the functions bodies don't have to be looked at us by it in most cases, but even where they are looked at, what they depend on is just much clearer. Okay, so those are some comments. I regret that I can't be there in person, but I'll look forward to seeing you next on Tuesday the 8th. Thanks for